Hello, I'm Chris Athanas. I'm a KMP developer. That portal, the tech support says they're coming out on Tuesday. I don't know. They keep telling me that, but we'll see. We're going to continue our journey on how to program from the ground up. And we're looking at software. But before we get into the software, I want to show some of the more important algorithms that computer science people talk about all the time, which is from this data structures visualizations. It's so first of all, let's do binary tree search, which is from this here, from these trees, how these are actually searched. And the best way to do it is just to see how they are, how you insert something. So let's just delete all these. Let's start over on this. So let's do an insert. So insert first one, value 1. That's the first node there. The root points to it. That's the root node. Let's do 2. Let's do 3. Go play with these animations. It's really important that you play with this stuff first to see what's going on with it, because if you just look at the algorithm or hear someone talk about how this works, yeah, it gets confusing really fast. So let's see if we can do a left node here somewhere. Yeah, there's a left node. So let's do 20, 230. Let's do that one. I'll do a right node because all these values are greater. So it's just greater, greater, greater. This one goes less. Let's do 3. Doesn't let me do decimals. So let's do 34. Where's that one gonna go? That one's gonna go. Let's beat the animation here. So everything's all less. Now, do you also see how it's getting unbalanced? Now, there's other types of trees that will automatically keep the balance. Like after it inserts it, it does something strange, or as it's inserting it, it'll rotate these nodes around. So that's something you got to know about. And here's the Dijkstra for traversing these kinds of data structures here. These node types where everything's going pointing all kinds of other stuff. This will show you how Dijkstra's run. So let's say run Dijkstra for 4. So it's showing you all this. He's trying to show you all the steps as it traverses from one thing to the next using a directed graph or an undirected graph, and you can see how this algorithm works. Instead of having to go write it out yourself, which you should write it out yourself if you really want to know how it works. But if you can just watch this and look at the algorithm, the code, what the code is doing. So let's go here. So we got undirected graph, like everything's connected to everything else. Undirected, there's no arrow. It's undirected, no arrow. Oh, here's directed graph. Oh, look, it's got arrows. It means this one goes to this one, this one goes to that one, and these two right here go to that one. Ooh, a directed graph. And then you have a small graph and a large graph. You can play with all these things that totally randomize it. So you can see how it works with different things. And then you have adjacency, list representation. So instead of using a node and pointers, it's using a list, an array that has a pointer. Each one of these array elements is a pointer to a linked list. Ooh, okay, well, I guess that's another way to look. I mean, it's all the same stuff. It's just data, pointers are data. And then here's another one where it's just using an array, a 2D array. It shows all the connections from one thing to the next. 5 and 1 are connected to 3. So you can see these different representations of how computer science people think about stuff. It's just all the same junk. It's all the same stuff, just representing it in different forms. And I really like how this student here has put this together. Matrix multiplications. Ooh, okay. So this is just how it just shows how it works. So scaling it shows how it goes through the multiplication, and it shows the calculation happening here to get the result. So this is doing a scaling by a factor of 4. So it's doing it for each one of these points. No, I'm rotating it a little bit. I'm rotating it 4 degrees. All right. So let me do 45 here. Let's start over. 45. What happens if I want to rotate 45 degrees? So it builds this. Here's X and Y coordinate of each one of these things, right? So that's doing this coordinate here, and then this coordinate here, and this coordinate here, and then it does a 45-degree angle. So first it's doing the scaling thing, and then it also does the transform at the same time. It's pretty cool to see how all that stuff works because it's really like people make it say, "Oh, it's a mystery. It's a total. It's just very strange how all this stuff works together." No, it's not. It's all just the same stuff. Oh, it's just someone's clever, being very clever, putting all these together in this way. Let's do another. Let's just start at 10 here. Let's start over. Let's do it 15 degrees and scale it at 15 degrees and scale it 2 times. And well, let's do it this way, and then we'll do the with the different. Does y is y up or is y down? Is plus y this way or is plus y down? Because in computer graphics, all the computer graphics people do it x with plus y down. Weird, but it makes sense because this is 0 column. This is 0 row, 1 row, 2 row, 3 row, and it counts down, right? This is line numbers, right? So okay, that makes sense for computer people. But math people, negative is this way. Okay, all right. So whichever way you want to do it. And this is really great that he's shows how do you rotate then scale, or do we do scale then rotate? And then there's a different matrix. This uses a different type of thing to do this, and it shows all the math happening right here, every little step along the way. How it does its thing. Super awesome. This is all how computer graphics work. That's all it is. And that's why these GPU cards, all they're doing is matrix math. And then all this matrix math is just multiplication in a special way. It goes this one, this one, this one, this one. It's like they show you here. So it's actually pretty useful to look through this before you go look at the algorithms, because the algorithms be like, what are you doing here? Why? Oh, it's just a convenient notation that kind of does 2 things at once. Oh, okay. It's just that. All right. And then here's sorting, right? So there's when I when I was coming up, they had a whole before they discovered quick sort, there was all these different ways of sorting, and people were arguing about which one's fastest and which this, and it was started off with the bubble sort, which is this one. Super slow, and it's like I think it's ON squared, maybe, because it has to go through this list twice in the worst case scenario. So it takes each element and compares it with each element as in the array, and then swaps at like a bubbling up. So that's why it's really important to see the animation, because the animation actually kind of refers to this how we're visualizing it in our brains. And before I saw these animations like this, I was like, why are you calling this a bubble? Because it like a bubbles each one element at a time. It's so slow. Holy, it takes forever. All right, let's try a different one. Let's do this one. How about the next one that was a big deal? Oh, the merge sort. You see how it takes each little section and then sorts each section and then sorts those sections? It's sort of like the first kind of recursion one that they came up with. And then they have the shell sort. And you should go play with these. And it's like, oh, it does these 4 at a time. So it's sort of like does it in recursion, but it does it in a slightly different way. And yeah, it eventually gets it all sorted. But you see how the CPU is only doing one thing at a time, and that the thing the CPU is concentrating on, or what it's comparing is he's showing you that line is where the CPU is at that moment. Let's see here. Shell sort. Is this one? Oh, okay. That kind of does a similar thing as okay. And then here's the selection sort, which wasn't very popular. I think this one happened right after Bubble. It's like a slightly faster version of Bubble sort. Not much faster though. Okay, and then of course we get to the quick sort, and it just kills them all. It just destroys them. And I getting towards a theoretical limit probably is a theoretical limit of how long anything could possibly take. But this is the fastest one, and nearly all implementations when you do dot sort is using this underneath the hood as a general case. So it's just good to know what people are talking about and why they made a big deal about it, because it took a long time to find this, for someone to find this. I'm not sure who found it, but it was definitely someone found it. So, and then there's also the searching, where search a linear search. This just shows how the computer does all this stuff. When you do a searching for something, it actually shows the code here too, which is really neat. So let's go search for this value, 317. So if the computer just does a naive linear search, just one element at a time, this is how it's going to do it. Boop. Okay, so it has to go through the whole list. What happens to the value is at the very, very end. With the worst case, it's going to have to traverse the whole list. But with the binary search, boop, 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 super fast. way faster because that's that log n search because it's like splitting it into two and then boop 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 because this is and this is just how it does a sort. It does a search on it, and it's interesting this isn't sorted and it still gets to it. So, or is it sorted? Yeah, no, it's a sorted order. No, I take that back. It is sorted. Yeah, to do a binary search, you have to have it be sorted. I take that back. My mistake there. So yes, this is a sorted list. So yeah, that's how that's so searching, sorting, and going through like Dijkstra stuff with the distances here. The same thing is it's just a regular graph with distances for each one of these edges or connections. Okay. So that is that. So we're gonna get into a little bit into how much time I got there. Okay, that's 10 minutes. I wanted to show that stuff because this is important. People talk about like it's a big deal, and it is sort of, but they make so much of a big deal about it. You just do dot sort now, and it's just it's all been abstracted away. But for a long time, people always like make a big deal about it. And then when you get to scale, right, when you get to like petabytes and stuff, all that stuff changes and you have to do it a completely different way. But the underlying ideas are still going to be used even in those implementations. Okay, so software, the easily changeable machine. So we're talking about machine language. When we talk about machine language, it's this stuff. So the big idea is logic gates can be built up to create a general purpose machine that can execute easily changeable programs called software. Easily changeable, meaning that instead of actually changing the hardware gates and rearranging them out, now we have them all like in RAM, and we just run through them and have a special machine that does a general purpose gate. That's all it is. That's where it came from. I was like, could we make this general purpose and not have to dick around with it, moving around the damn chips? All right, so the software can be changed anytime, even when it's running, right? And because that's how all these compilers and assemblers are just changing code while it's running. It's nothing magical about it. And to change the behavior of the machine instead of physically creating a new machine for that specific task. Okay, so it's also important. It is important to know that any piece of software can be implemented in hardware. So when I was doing my computer company back in the 90s and the early 2000s, I was approached by a company that was using a field programmable gate array to take my software, my little filter, my like video filters. You can see what I did on my GitHub if you want, and to put them into hardware to speed it up by a factor of like 10 or 1,000, depending on what I was doing at the time. I was like, nah. So they're using these field programmable gate arrays, which is basically hardware versions of software. And I want to just give a little, just kind of an insight that you can do both ways. So field programmable gate arrays is software programming hardware. There's the special kind of hardware. It's just a bunch of gates all linked up in a grid to do a function. Go ahead.
So let's say that you write some code. The way this code usually works is that it's compiled into instructions that run on a processor. But you can also write it a little differently, and it will get synthesized to effectively run on an FPGA. This kind of code is called a hardware description language. Synthesis is the process of mapping this code into physical hardware blocks.
Yeah, just wiring up these blocks of these standardized gates, like it's like a NAND gate, but it's a little bit more than that. But it's basically that. It's like a built-up specialized block, and then they wire it up on the board using these software tools. That's all it's doing.
These hardware blocks are comprised completely of registers and logic gates. And, or, nor, not, XOR, and XOR.
That's the same stuff.
The trick is that logic gates can be implemented using lookup tables. So if you put together a bunch of lookup tables and make them programmable, and then you add a switching fabric that can connect them all together.
A switching fabric is just a routing fabric. It's just wires. And what they do is they blow fuses where they don't need connections. So they'll blow a fuse. That's why they're like one-time use. Now there's other ones that you can reuse them and reprogram and all stuff like that. But the general idea was in the beginning was you blow these fuses, you'd build these chips, blow these fuses, and then run it on a regular current and regular power to do this. It's like very clever.
And then you allow the user to reprogram the lookup tables to whatever we want. Then now we have a single device that can run whatever code we want. We call that device an FPGA.
Right. So, and it's really cool to visualize the difference. Here, let's go and look. Let's start this over. Don't worry. I recommend going and checking out this and just looking at what's all going on, because this is actually a very accurate description of the difference between a regular CPU and this FPGA thing, which is a pseudo CPU. uh, it's really neat, and all it is at the bottom still just NAND gates, OR gates, NOT gates. There's nothing special in here. There's no magic. It's RAM up here. It's going through the CPU at one instruction at a time. Blip, 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 blip. Refilling up data here. Yeah. So go watch those again if you can. They're super useful. Great to have those animation tools available. So machine code is the language of the logical operations of the CPU that the CPU can perform. And it's just human cleverness, right? Pardon me. Anything that the computer can do is just a combination of these logical steps, right? Series of gates. Instead of having the gates wired up, they're in a series of steps, and we store the results into these registers that are then used to program other states. And it's all up to the cleverness of a person going, okay, how can I use this to solve a problem in a series of steps? So anything that can be like a defined series of steps and with Boolean logic can be put into the machine. That's why it got so popular, because a lot of stuff that we do as humans can be done this way. So the machine hex values, opcodes, are unwieldy for people to remember. So it's usually just like this number, some random number that's the opcode, which is just a binary digit that goes into the machine as inputs. And so to make it easier to remember that stuff, we use mnemonics, easy for me to say. And that's how we, use the commands for load, store, add, subtract, compare, jump. That's where they get those things from. They're just numbers to the computer. I don't care. It doesn't care. It's just a signal to set up a binary sequence. Okay. So we gave it these names and numbers, and that's really it. It's actually, this level of programming is super annoying. It's very fast, but it's actually, unless you're doing systems level engineering, there really is no reason to do any of this anymore. You'd rather if you want to get down to the metal like this, you should be using C or, God forbid, C++. But C is probably what you want to do for this level of stuff. I don't think you need to use C++ for this. You should be using another language like Java or something that's a little more portable, and unless you just really need that tiny 0.7% more speed. Okay, understood. Representation of data in memory. So big idea. If we represent numbers in binary, then you can perform logical operations to build complex arithmetic operations. And I apologize if this sounds a little bit repetitive, but it is important to have it coming from different angles, which is why I'm talking about it in this way. And this way it may repeat a little bit, because by saying it a couple of times, you're going to get different angles. That's why I'm doing this. Okay, so example. So binary coded decimal. So binary to decimal conversion. So it's just, this is integers, right? So this is column 1, column 2, column 3, column 4. And it starts from the right to the left. And this is the least significant bit. The one that's the lowest number, least significant. The math people. So this is the 1's column, the 2's column, the 4's, the 8's, the 16's. So anything that's a number in this thing gets added. And here's how you do the math. So for the example, 110, it's 1 times 128, 1 times 64, 0 times 32. You add all those up, 128, 164, and then you get the number 218. So that's integer, unsigned integer. Right. So 8 bits are called a byte and can represent 256 different values, usually noted 0 to 255, because computer start counting at 0. And that can be a problem for beginners. Like, why is it important? It is important. We start counting at 0. Not 1, 0. A byte is the smallest unit of memory that can be addressed by that particular CPU. I guess I should change that to not that particular CPU, but like it means a word. A word was the smallest unit of memory, and in microcomputers, I'm going to change this in a second. A A byte is the microcomputer. When the microcomputer came along, they're like, "Ooh, we're gonna get so small," and they came with a new word for the instruction for the word for the computer word, which is the smallest unit of a number of bits that the CPU of that design can address. So they usually were at that time were like 16 or 32 bits. So it was like this big word, but we're a microcomputer, so we need to go down smaller. So they made a new word called byte to represent this really small thing, right? Because that was like revolutionary at the time. It's like, what do you mean you can just do just 8 bytes at a time? That'll work. And so that's why this thing came out. And at the time, this game came out, which was made by computer people, of course. And this is my my conspiracy theory about Pac-Man with the little dots. He's actually eating bytes, or bits. And then if he's eating four of these at a time, it's just a nibble. And that's actually an official word for 4 bits. And that's the value 0 to 15. Don't even think it's 1 to 16. No, don't you ever. It's 16 values, yes, but we start counting at 0. Hexadecimal counting. Okay, so because these are super unwieldy, especially when you start to get up to number digits, it starts to get a little. It's like, come on, all this stuff gets super annoying. So we decided to use hexadecimal, which instead of 10, 11, 12, 13, 14, 15, we have A, B, C, D, E, F. That's it. That's hexadecimal. Ooh, it's hexadecimal. Ooh. That's all it is. It's just a way to pack it in. So it's packed into 2 digits instead of 3 or 4 or 8. That's it. So every computer company had a different way of representing the alphabet and numbers. They all did it completely differently. And some didn't have things. Some didn't have certain symbols. Some had certain symbols and didn't have others. It was a cluster F. Total mess. And so the ASCII standard came out in it's like 68 or something, 65, 63, somewhere. It was after a lot of gnashing of teeth, and they had to come up with something that was obviously completely better. So they used this binary digit thing to categorize these different categories of characters. So like lowercase had a certain category here, uppercase had a category here. Symbols had a category here. Numbers had a category here. Notice it starts at 0. The binary digits here are like the lower digits and the upper digits. And you can see that 0. It's because a lot of machines were still using machine language at this time. It made a lot of calculations and display and like converting numbers to byte to decimal and back again. Super convenient when you had it set up like this. So you could just like ignore these top bits and just use these bottom bits just to represent the numbers 0 through 9. And here's everything's in alphabetical order here. You don't have to do any mapping. All that kind of stuff was built into it for lots of reasons. And this just went along. And like if you want to capitalize a letter, all you have to do is change 1 bit, and it goes from lowercase to uppercase. It was that kind of stuff. So that's why eventually this became adopted everywhere, because it was just made so much more sense than everything else. But it was a battle. And that's been a theme throughout computing. People would start off with something just to get it done. There'll be a bunch of implementations of it. It'll all be done. Some will be done well and other ones will be really poorly. And everyone suffers with it until we go like, okay, guys, we got to get together. We got to get together here and standardize some of this. This is crazy. When I go to another company, we're doing it completely differently and everything breaks, and all the software I wrote, I have to rewrite again, and we're just wasting all our time doing this stuff. And they're like, okay, we'll do it. But I get to be in charge. The whole time. But I get to say how it's done my way. Then we end up with Java. Or C++. What a mess. Anyway, okay. Anyway, so ASCII table using hexadecimal. So that's the binary one. That's why it became popular. In hexadecimal, it doesn't really make as much sense. But if you're going to be looking through data, it's all going to be hex. So when you're looking through the data, you're like, what the hell is all this stuff? If it's a hex, it's hex codes, whatever, you can then go, look up a table like this. And most of the time, the editor is going to give you all that stuff. But still, if you do the direct data dump, all you're going to see is these hexadecimal numbers, and it's going to be usually be in ASCII. Sometimes it's Unicode, but usually with the computers, by the time it's doing the processing, oftentimes it's going to be this pure ASCII. So these are all special codes for doing communications, because all this stuff was really designed for transmission of data over lines. This was kind of the idea also behind it, is like, hey, we need these computers to talk to each other. And if they're going to talk to each other, we have to have a communications language. So this is the early version of HTTP, or hypertext transfer protocol before the internet. Just getting characters from one computer to another that didn't have the same character set was a big deal. It was a big deal. So they made it so. So all these things are like the null character. Oh, 00 is the null character. Start of header, start transmission, end of text, inquiry, acknowledge. Bell means this was control G. And if you go up to an old computer and do control G, it'll go ding. This is the bell. So a lot of times, even in the old TTY terminals, they would do control G, ding, 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 to get the attention of somebody. If the operators, if you had somebody that was trying to, because you could do little chats on these Unix things, so you would to get the attention of the guy. You go ding, ding, ding. Silly. Computer people are funny. All right, the minimum components of any computer system. Okay, so here's the computer block diagram, right? So here's your crystal, which is just a little piece of silicon. No, it's a little piece of silicon, right? Quartz. Yeah, it's just quartz. When it's got like a shape like a little U-horn, and if you pulse it with a piece of electricity, it'll go woo 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 woo. it'll vibrate at a particular frequency. Well, they shave it until it's perfectly at the frequency that it always does the same frequency the whole time. So that's what's really wonderful about these silicon crystals, is we use them for all kinds of stuff. They're super useful. It's just a little piece of sand. So that crystal drives a clock chip, circuit. What all it does is does a pulse. So every time the chip does this little singing, or every 10 times or 20 times, it goes boop boop, puts out a little 1 0 for the clock, and that sets up the internal clock for this MPU, which is the same thing as a CPU. Like they had to make it different back then. Microprocessor unit. It's like it's just the same as a CPU, same stuff. And then it has a bus, right, to get data from the ROM, from the RAM. This is like the boot code, or the firmware. It's the permanent code that's super hard to change, or doesn't change at all. Will never change. And then the RAM, the stuff changes all the time. That's just more transistors, and then programmable I/O. It's just a standardized interface to talk to peripherals, which are just more transistorized stuff, particular configurations that are specific for a particular task, designed by people, usually as a product. And then we have these control lines. It's like, I want to read from here. I just want to read from here. I want to put this out here. So all that has to be controlled. And then there's the address. Like, I want to get this address. I want to get that address. And this is the data coming in or going out. So that's how that's all set up. It's all still just transistors and little packages of logic gates. That's all it is. It's nothing magical. And the microprocessor, microprocession. I gotta fix that. Is the brain of the computer? I hate that. I need to change that. I think ChatGPT put that in there for me, so I gotta take that out. It's not the brain. It's just where all the actions where it takes the instructions, actually processes the instruction, and then gets the result. This happens in here. That's all. So this thing right here is this. Inside here this is the block diagram. Computer people love block diagrams. It is helpful to get a high-level view of what the hell's going on. Here's that address bus we were talking about. Here's that data bus, so all the data comes in, the actual values at the address. So at this address, we'll either put data into it or get data from it, depending on what you're doing here on this control bus. And that's in the control unit. So that's really the heart of the machine that times everything. When that clock pulse comes in, it goes, oh, okay, now I get an instruction. Oh, now I go decode the instruction. Oh, now I go, do what the instruction said. Do you get that thing? Oh, now I put it into the ALU. Oh, now I get the result. Oh, and it's just everything in the O is the next instruction that a programmer put together. And like, here's the data coming in, puts in the X register, the Y register, And this is the ALU, and the control unit says, okay, now do an OR on that, or do an add on that, or do a subtract on that. And then it says the result will be here, and there's an accumulator. And there's a little flags register here too. And then the control unit just reads that and goes, oh, okay, this is the instruction that's being read, and this is the program counter. This is the current place in memory where it's executing. And that's it. Now, modern microprocessors take this to extreme level and put caches everywhere and make it super, look aheads and try to figure out what the next instruction is going to go or the next series of instructions, and then build up that ready to go. And then if that branch is taken, it swaps in that. And if the other branch is taken, it swaps in that. That kind of stuff. It does that, but you don't have to worry about it. It's all abstracted away, unless you want to get down into there. Do you really want to do that work, though? Is that really where you want to spend your time? I don't know. Some people are super into that. I would rather do business applications. That's all computer engineering, right? When you start to dive into that, the systems engineering, computer engineering, very linked together. Ooh, I think it's about to be abstracted away, honestly. I don't know. Maybe, I don't know. I'm not interested in that. It is good to know how it works. But if you're interested in that, that's a different tack. That's a different tack than that this takes on. You're probably already down the guts anyway. All right, so the memory address register. It's just like, okay, what address does this current CPU or the instruction, what address are we trying to get? It just puts it there temporarily. Ooh. So what address is this control unit for the instruction it's processing? What address is it using? Ooh, and the data comes back on this. And it goes into the X, it goes into the Y, depending on which one the control bus is setting. Okay, so it's Ben Eater's course. If you really want to know how all this stuff is put together, if you go through Ben Eater's course, you will know how this all works. And you won't have to worry about it. We're going to use it anyway. So I'm at about a half an hour. I'm going to keep it to half an hour episodes, try to. We're going to go into the clock next.